So we're going to continue working through our application examples. We're going to do exercise 2 on this handout, models of exponential growth and decay. And so let's move this up and I'll write below. So in exercise 2, we have a bacteria population that starts out at 8,000 and doubles every 5 hours. When this 5 hour, doubling every 5 hours, 5 hours is called the doubling time. Every exponential growth situation is going to have a doubling time similar to what we're going to see in this example. So let's do part A. What's the population when t equals 5 hours, 10 hours, 15 hours, 20 hours? I'm going to set this up as a table with t and f of t. So t is hours, and f of t is number of bacteria. And there's not much math to do here. It's really we're just observing what doubling time would mean. And I also want to put t equals 0 here on my chart because we're starting out at 8,000. So at time 0, we have 8,000 bacteria. At t equals 5 hours, so every 5 hours the population doubles. So if we double 8,000, 2 times 8,000 is 16,000. And then if 5 more hours goes by, so at time 10 hours, the population doubles again. So we're going to double 16. 2 times 16 is 32,000. 5 more hours go by at 15. Double, we get 64,000. 5 more hours goes by, we get to 20 hours. And we're going to double the population again. 2 times 64,000 is 128,000. So that's just meant to illustrate the issue of what's going on here when we talk about a doubling time for a population. Okay. Now what we want to do is we want to find a formula. And in part B, we're going to try to find an exponential function of the form f of t equals a0 e to the kt that matches these points, this data. Now finding the function means we have to find a value for a0, and we got to find a value for k. For a particular function, a0 will be a specific number, k will be a specific number. And you know, we already know what a0 is. We've observed now several times that a0 is the function value when you plug in t equals 0. So from our table here, we know a0 has to be 8,000. Okay. And now what we got to do is we got to try to find k. And what you do is you use a different point. And it doesn't matter which one. I'm going to use t equals 5 to find k. I really could have picked any one of these points, but I'm going to take the point where from our table 5, 16,000. So what we can say is that f of 5 is 16,000. And now let's, again, we're going to use our formula. F of t equals a0 e to the kt. So f of 5 is going to equal a0. We already know is 8,000. E to the k we don't know yet. times, instead of t, I'm going to write 5 because we're plugging in 5 for t. I'm going to replace the left-hand side with that value, 16,000. 16,000 equals 8,000. E to the k times 5, I can write as 5k. And now we got to solve for k. So here, once again, we're solving for a variable and an exponent. So we got to isolate the exponential. I'm going to start by dividing by 8,000 equals e to the 5k. And 16,000 over 8,000, that simplifies all the way to 2. 16,000 is just 2 times 8,000. So I get 2 equals e to the 5k. And so now I can take ln of both sides. Ln of 2 equals ln of e to the 5k. So ln of 2 equals 5k times ln of e. That's by the third law of exponents. The ln of e is 1. So ln of 2 is equal to 5k. And now I'm going to just move over a bit here. To solve for k, I'm going to divide both sides by 5. Ln of 2 divided by 5 is k. And I need a decimal here. And so let's see, 2 ln divided by 5 on my calculator. So, I see a long stream of decimal value here. Decimal places, 0.138629436 equals k. You don't have to write that much down. We're going to round off here, and always round off at like 4, 5, or 6 decimal places. If I go with 5 here, so we don't have a rule, just the more the better, but I'd say 5 is plenty. Okay, if I round off at 5 places here, I get 0.13863 is our value of k. Round off at 5 decimal places. And now I'm not done yet. I have k, I have a0, but our goal was to describe this function in f of t form. So we have to go back, and we have to write our function out. F of t equals, instead of a0, I put in the value of a0, which is 8,000. E to the, instead of k, I now have a value for k, 0.13863. And then I go back to t. I put t back in here because now what this means is I can use this formula to calculate other function values now, not just the few I have in my table. So just make sure you realize that's the formula we're after here, that f of t equals 8,000 e to the 0.13863 t. Okay. And that's like a big deal, this part B, to take that given information about the doubling time and turn it into this exponential function, f of t. Now let's continue on that exercise. There's a part C and a part D. Part C is to evaluate and first they say f of 0. Well, you should know f of 0 is 8,000, right? And now you're going to say, wait a minute, f of 5, we already set up that table, right, on our part A. I just want you to confirm here that the function we came up with really gives us the values that we would expect. So I'm going to plug in 8,000 e to the, now I need my decimal, or I'm just going to, I got 0. Oh, here it is underneath. Sorry, I got too many sheets of paper floating around. There's our function down at the bottom. 0.13863 times 5. And so we're thinking that should give me 16,000, right? Well, let's just confirm that with my calculator. So 5 times 0.13863 equals, take e to that power and multiply by 8,000. Now I don't get, notice I don't get 16,000 exactly, but it rounds off to 16,000 is a whole number. F of 10 is 8,000 e to the 0.13863 times 10. One, 3,863 times 10 e to the power times 8,000. And again, I get something very close to 32,000. Rounds off to 32,000. F of 15. So notice how this funny decimal value for k is giving us these output values we want. 15 times 0.13863, 0.13863 e to a power times 8,000. And but at f of 15, if I round off, I actually get 64,001. And if you notice f of 20, one more, we're just going to do 8,000 e to the 0.13863 times 20. 20 times 0.13863 e to the power times 8,000. I get 128,001. And I just want you to think for a moment, why is this isn't coming out quite the way we wanted, right, from our part A part of the problem. And these are off a little bit. These values that we're getting in part C, because we rounded off our value of k. If we had used more decimal places for k, we'd be getting more accurate values here. And it's just not practical for us to keep lots and lots of decimal places for k. So it's okay to round off, but then just be aware that when you continue on with the problem, your results may, once you round off somewhere in a problem, everything along the way may be rounded off a little bit from the actual values of the values we want. Okay. So there's one more part to this one, part D. What we want to do is find out when the population reaches 100,000. So find t for when f of t equals 100,000. I can kind of guess that this is going to be between 15 hours and 20 hours, right? It's going to be between 64,000 and 128,000. But now let's use our formula. f of t equals 8,000 e to the 0.13863 with a t in it now, because we're going to try to find the value of t. That makes the function value come out to be 100,000. And here we go again, solving an exponential equation. We got to divide by 8,000. So in all these applications, this is a process we're going to do over and over again. Probably the single most important operation working with exponents that we've learned. I can reduce this guy a little bit. It's 100 over 8, and you don't have to, it's okay to use a calculator. And you don't have to write fractions. It's actually 12.5 equals e to the 0.13863 t. Now I'm going to take ln on both sides. And I'm going to write this just slightly differently than we have been, because we've seen this pattern occur over and over again. Instead of calling this an application of law 3, which we could, I just want you to see that ln and e cancel each other out. And that expression in the exponent comes down to earth, 0.13863 times t, and is equal to ln of 12.5. So in other words, this is what's always going to happen. It's just going to look like this, where as if ln and e cancel out. And in fact, ln of e to any power is always equal to that power, because ln and e are inverse functions, so they're always going to cancel out. So we can just take this shortcut and avoid having to go through that law 3 of exponents each time. And now I have ln of 12.5 divided by 0.13863 is equal to t, and I gotta use my calculator. .863 12.5 ln divided by 0.13863. And it looks like I'm getting, I have to round off again. I'm going to round off at 18.2 hours. And that makes sense, but it seems like a reasonable answer since it is between the 15-hour and 20-hour time. So there's our answer to D. And let's see, I would like to, in this video, move on. So that's the end of that problem, okay, where we made use of, we found the formula for this function and made use of it over and over again. I'd like to go on and do exercise 3 before we quit the video. So it shouldn't take us too long to add this on. Exercise 3 is to find the doubling time for the population in exercise 1. Find the doubling time for f of t equals 90,000 e to the 0.08 t. So I'm going back to that exercise 1 function. And to do that, really, we can pick, to find that doubling time, we can pick any two points well, where we see the population doubling. So we know at t equals 0, the population is 90,000. What we want to know is at what time is the population going to be double that? 180,000, right? So here we want to find t when f of t is equal to 180,000, which is double our initial population value. So I'm going to take my formula for the function f of t equals 90,000 e to the 0.08t and set f of t equal to 180,000. And solve for t. Once again. And now divide by 90,000. Here we go through that same process again. Oh, sorry. Sloppy. 180,000 over 90,000 equals e to the 0.08t. I can reduce this fraction. That's just going to be 2 here. 180,000 over 90,000 is 2 equals e to the 0.08t. I can take ln of both sides. Ln of 2 is equal to, now here again, ln and e will cancel out. I have just 0.08t. I can apply our shortened form of that step. And so ln of 2 over 0.08 is t. And I got to check that on my calculator. Let's see what we got. 2 ln divided by 0.08. Looks like I get 8.66 is approximately equal to t. And exercise 1, that was years. 8.66 years is the doubling time. So going back to my chart here, I just want to say we found out the t value here is about 8.66. If I went through another 8.66 years, we're not going to check it. I won't make you check it this time. Another 8.66 years is going to be 17.32. That's just 8.66 plus another 8.66. I just added those. I know at 17.32 years, this population is going to be double 180,000. I think that's 360,000. And we're going to stop, I think, in there. This has been a long video. Just, there is a statement about the graph at the end of this handout, and I just want you to see the shape of exponential growth function graph is like so. I'm going to talk a little bit more about graphs at the very end after we do all the word problems. So I'll have more of an explanation about this shape. But just notice it's basically our exponential function shape. It's just the dotted line means the negative portion of the graph isn't really relevant for exponential growth, because usually we start at a certain time and just move to the right. But why the graph has this shape, we'll say a little bit more in another video after the word problems.